Hello, FOG students. Welcome to FOG Studies. This is the first lecture of many that will follow to get you a basic understanding of FOG and then an understanding and ability to engage in the research that I've been doing for over 15 years and that you'll be able to jump onto relatively quickly. I'm going to give you a little bit of background on FOG just to start so that you have some idea of what fog is, and then eventually how we can measure it. And I should say a little bit more about the class first. I have the syllabus that's on Canvas, and I think you'll be able to find it because I already sent the link to Canvas, so hopefully you can find that. My plan is to have regular short lectures, probably one a week, with optional times to meet that I will be sending you a when is good type of poll to come up with a time that works for as many of you as possible. It's not mandatory, but if you want to meet and meet with others, that would be the time that would be picked. And it's okay if you can't. You can do everything online, talk to me and or talk to others in the class if you would like to. And I highly encourage people to work together in small groups when it comes to the projects, and we'll talk more about that later. Pairs, I think, is really good because then it's easier to coordinate meeting with somebody else, and it gives you somebody else to talk to about some of the ideas that we're going to talk about in here. And you can always talk to me as well. I'm happy to talk to you outside of whatever time we come up with. If you want to talk to me individually because you just want to talk about fog or you have some questions or anything like that, we can come up with a time that you can meet with me. So coordinate with email. That would be probably the best way to try to come up with a time to meet with me if you want to meet outside the optional time that we're going to come up with. Part of what you're going to be doing this semester is working on a project based upon my ongoing network of what I call standard fog collectors. I call them that, and that's what they're called. Here are 5 of them. There's actually a 6th one that's down. It's now up, so there's 6 of them at the moment. And these are ones located on campus, but I have dozens of them located in different places around the state and certainly around Monterey County. So this is just an example of them. That tall pole in the middle with looks like a little arrow on top of it, that's actually a meteorological sensor called an anemometer. It's a sonic anemometer. It measures the wind speed and wind direction. And there's other meteorological devices that are there, and having access to meteorological data is also very critical in looking at fog, in addition to measuring how much water we're getting from fog. And we'll talk about all of that later. But this is just one picture taken of one set of fog collectors available to us, whose data we'll all be able to use. And within this class, not only are you going to have the opportunity to work with data that I've been collecting for years and I continue to collect, I want you to have the opportunity to be involved with either the deployment of these instruments, and we'll be deploying them actually this May, if not sooner. I am going to be deploying a bunch of them and changing things around at the site I just showed you and at another site with colleagues from the University of Virginia. We have a contract with them to compare different types of fog collectors. There's going to be a lot of work going on even before the semester's out, I suspect. And in order to deploy them, of course, we have to build things. So cutting pipes, stitching on mesh, things like that, you'll have the opportunity to do if you would like. That's the construction. And then the maintenance, sometimes fog collectors fall down. We also have to collect data from them every so often. Some of them, you have to actually physically go to the instrument to collect the data. Others of them, that's not true for. But we'll be involved with that too. So you'll have plenty of opportunity to be involved with one or more of these. And that's something I want you to have the experience of through this independent study opportunity. And we'll talk more about that as well. Now I want to tell you a little bit about what is fog. This is kind of getting more into the scientific background content of what is fog. Well, fog actually has 3 ways that it's defined. I think it's kind of an overlap to some extent of these 3. Fog is a cloud that is in contact with the ground. So it has to be touching the ground. A cloud. So in other words, if you see a cloud on a mountaintop, that's often where you see pictures, you see a mountaintop, you see it surrounded by a cloud. At the mountaintop, it would be in fog. So that would be considered fog there. But to us on the ground, we look at it and say, hey, that's a cloud. So even there's a little bit of ambiguity, but I would say if it's in contact with the mountain, then at the point at which it's in contact with the mountain, I would say there's fog there. Like clouds, fog consists of tiny droplets of water, and droplets have a diameter. They're approximately spherical. That's what we're going to assume. And that the diameter of them can be anywhere from 1 to 50 microns. Now, what's a micron? A micron is 1,000th of a millimeter. And you know what a millimeter is? It's about that big. There's 1,000 of them in a meter. So the droplets are not big. Often you can't even see them. Sometimes you can see them, but I'd say a 50 micron droplet you can probably maybe just barely see. But a 1 micron droplet you would not be able to see at all. If you have enough of them, though, it'll appear like it'll appear like fog. And that leads to the third definition. The combination of the first two has to lead to a visibility of less than 1 kilometer. Then it's defined to be fog. If you have visibility of greater than 1 kilometer, say 2 kilometers, 3 kilometers, but it's still kind of hazy, then that's haze. So that's the distinction between fog and haze. There's a lot of also frequent misunderstandings that I have to correct, or I hear all the time. Sometimes I can't even correct them because I don't get to it with the person I'm talking to. But I want to cover them now. And so if they come up, we can address them when we're talking so that we're all talking the same thing. You'll often hear, well, the fog condensed on the surface. People say that all the time. I said it too when I was first learning about fog and fog work. Fog does not condense. Fog has already been condensed. It's already a liquid droplet. Condensation refers to the process of a gas becoming a liquid. Fog is already a liquid. It's tiny droplets. And it had to condense to become that liquid. But fog itself doesn't condense on surfaces. It's just that the little particles that fog has to form upon, the water condenses on those, then you have fog, then it's droplets. And those droplets collide with surfaces. And then the droplets stick on the surface and they start to get bigger and bigger as more and more of the little fog droplets hit upon the surface. That is how fog water is collected. That's one misunderstanding that often comes up. Another one is that fog is not a vapor at all. And that kind of ties to number one. It's already liquid. It's just that it's a lot of tiny little droplets of liquid, many, many billions of them, depending on the size of the volume you're talking about. But we'll talk more about the number of droplets per given volume. I have an instrument that can measure that. And the amount of water per given volume. When it exceeds a certain amount, we consider it fog as well. So there's a bunch of different definitions we can use to define when we actually have fog, in addition to the 3 that I gave on the last slide. Another one is that fog doesn't really fall. It does, I guess, but it's very slowly. And the reason for that is kind of like if you've ever gone skydiving, and I did do it once. I'm glad I learned a lot from doing it. When you're an object falling, the air actually resists you. If you ever go skydiving, at first, when you first jump out of the plane, you feel like you're accelerating, like you're on a roller coaster, and you feel that churning in your stomach kind of thing, and it's really exciting. And then after just a few seconds, it just feels like there's a wind blowing past your face. You're in what's called free fall at that point. And you're beyond that. You're actually in what's called terminal velocity. You're in free fall once you jump out of the plane. Terminal velocity is when you're going as fast as you can, because the air itself is pushing against you. So what happens is when you first jump out of the plane, you accelerate. You're not moving at all vertically when you first jump out. Then you're moving faster vertically downward, and then faster and faster. That's called acceleration, where your speed increases. But you reach a certain point where your speed is as fast as it's going to be. And for a person falling, it depends on your orientation, but it's going to be about 110 miles an hour vertically downward. When you're moving that fast, the air is pushing you up, and it's pushing you up in such a way that your speed is no longer increasing as you're falling. And that's a situation called the terminal velocity. You reach terminal velocity at that point at about 110 miles an hour. Or that would be about 55 meters per second. Now, rain, depending on the size of the droplets, that also reaches a terminal velocity. Otherwise, it would just keep going faster and faster and would hit the earth the speed of a bullet or more. But it doesn't. It reaches the earth, and it's hitting the earth at, depending on the size of the droplets, several meters per second, maybe 5 meters per second for the big droplets, And the smaller the droplet gets, the more the air molecules impact it at a lower speed. So small droplets have a lower terminal velocity. They don't move as fast falling. So drizzle, for instance, falls at a much lower rate than rain. You don't feel the impact of drizzle. You can feel that maybe you're getting wet. Drizzle droplets are a lot smaller than rain droplets. Fog droplets are even smaller. They are so small that their terminal velocity is on the order of several millimeters per second, if not less, depending on the size of the droplets. The 1 micron droplets, they're barely moving at all vertically. The larger ones are barely moving at all either, but over time, they'll slowly be descending. And this is very similar, for instance, if you put cornstarch in a bunch of water and the water gets cloudy. It's the same kind of thing for fog with those little droplets of water in the air as cornstarch is in liquid water, a cup of water. These are situations in chemistry that we call a colloid. We have kind of like a suspended material in a liquid or in a gas. And fog is like that. And as a result of the fact that fog is not falling vertically, it doesn't hit the ground like rain does. Rain, you measure the volume of rain in terms of, you'll often see, oh, we got 1 centimeter of rain. Well, centimeter isn't a volume. Meteorologists will often report that. Not only meteorologists, anybody who measures rain will talk about how many inches or how many centimeters of rain we got. That's a perfectly valid measurement because it means that over all the places where the rain fell, if the surface were not porous and if the rain didn't evaporate, if you just could add up all the rain, you'd have a 1-inch layer of rain on that surface if you had 1 inch of rain that fell, or 1 centimeter of rain, or however how much rain fell, given in whatever units it's given in centimeters, inches, millimeters. You'll have that depth of rainwater. That's a lot of water when you think about it, if you look at the whole area. So we're talking, millions of gallons of water for rain. Fog's different. It's not falling so much vertically. It is a tiny bit, and so there is an impact on how much fog maybe is falling and hits the grass or the surface of the earth, but it's nothing like rain. Where you really collect water from fog, or where it is collected, is when you have a vertical structure and the wind blows the fog such that the fog droplets impact upon that vertical structure. Then you have more accumulation on that vertical structure. But still, the total volume that you're going to get of fog water is nothing compared to the amount that you're going to get from falling rain. And that's another area of misunderstanding with fog that I'm hoping is clear for you even now. One way you can kind of distinguish fog from rain, this is kind of fun. One of my friends, my colleagues here, who's not a fog scientist, noticed it, is if it's on a foggy day and you're out in the street and you see trees overhanging the street, fog and when it blows, is going to impact the leaves, collect on those leaves as droplets, and then fall down. So beneath the tree, it's going to be wet, assuming the tree is, completely in the fog. If it's in the forest, you have other trees that might be blocking the fog. It may be harder to see this. But if you have an isolated tree and the fog hits it, fog's going to hit the leaves of the tree. Beneath the tree is going to be wet. But outside the leaves of the tree, it's really not going to be very wet. Maybe a little bit because you get a tiny bit of the vertical motion of fog, but very little. Rain, on the other hand, if you have a light rain, beneath the tree is where you'd want to be. If you want to stay dry, you go up beneath the tree, it's going to be dry. Outside the tree, the ground is going to be wet because the rain's hitting there. It's not hitting within the tree structure. So that's another distinction between fog and rain, which is very interesting. It's a lot of room for thought there. Another little fun fact about fog that a lot of people don't know about, but it's also a heavy area of research for those who do, is that the water in fog, believe it or not, is actually heavier than the water in rain. The reason for that is fog consists of the first molecules that condense or deliquesce out of the air onto tiny microscopic particles that either fog or rain rely upon in order to grow. So you get a little bit of these molecules of the heavier water that have isotopes of oxygen and hydrogen in them. It's just 1 in thousands in rainwater that have that, or in water vapor. 1 in thousands of molecules of water are going to be slightly heavier. But it's those slightly heavier molecules that are going to be the first to come out of vapor phase into liquid phase. And that's going to be what's in fog. So fog tends to be a slightly heavier water than rain. And there's plenty of studies that are looking at the really close measurements of the mass of water and able to determine isotopically that fog is actually heavier than rain. It's kind of ironic because it's floating there. but it's not heavier on the point that it's going to cause it to fall faster or anything like that. But it's slightly heavier. So fog is going to tend to have higher isotopes. That's one way of distinguishing fog from rain. And even in the water table, distinguishing how much of the water table might have come from fog, what percentage of it. And the last slide I want to give now, and then I'll end this lecture for now, and I'll tell you about next steps, is why would we want to even study fog? Hopefully you have some reasons because you're taking this class right now. Fog is interesting. I'll give you a few reasons here. You may come up with others, but there's quite a few here that it's not going to take long, but there's, I think, strong rationale to study fog. One is that fog and clouds are really cousins, or maybe even brothers and sisters. In a sense, they're one and the same. Fog is a cloud that's touching the ground. Studying clouds is incredibly important in meteorology and climate science as well, because clouds have a huge impact on our climate. How much energy hits the earth. There's a lot to think about regarding clouds. Clouds are also expensive to study because you have to typically fly in a plane to get to them. And it's hard to stay in a single cloud for very long. Fog, on the other hand, is on the ground. It's much cheaper to study. I don't need an airplane to study fog. I can do it from some of the ways that we're going to be doing it. So it's a low-cost way to study clouds. So that's one very useful rationale for studying fog. It gives us more knowledge about clouds. And we'll talk about the different types of clouds and how fog is like the lower clouds, not the upper cumulus clouds, but the lower stratus clouds is really what fog is most like. Fog and clouds, of course, are both impacted by and impact climate change. So in studying fog, we can learn about what effect our climate will have and also how the climate can affect fog itself. So it's important in climate studies as well. Fog has impacts on ecosystems. It brings moisture to ecosystems, or it doesn't if it's not there. And so since some ecosystems rely on the moisture from fog, it's a really important tool for understanding what's going on in our ecosystems, and fog is an important vector for providing water to many ecosystems. Fog is also important for the cycling of nutrients, chemicals, microorganisms, and all sorts of other materials from one place to another. And we'll talk about that more, but I'll just kind of, without giving you a whole lot of specifics, imagine all these tiny little droplets of water and chemicals in the air. Chemicals enter the water gets blown by the wind. The chemicals or other materials can then be present in other places where they may not have been able to move as easily if there wasn't fog. Fog also has huge impacts on transportation as a result of how visibility is affected by fog, which in turn impacts safety. One of the first places I learned that people were interested in studying fog was somebody from the San Francisco airport who I met in the 90s when I was working on a different project, who was interested in understanding the effects of fog and how to better predict fog to help people at San Francisco airport schedule planes better. Because when it's foggy at San Francisco, they can't have both runways open because of how difficult it is for the planes to see the runways. So it actually impacts travel throughout the whole country, even places where there aren't fog, because San Francisco is such an important hub. And this is true for other airports as well. And also driving. Those of you from California Central Valley know that when there's Tule fog, it's very difficult to drive through it safely because it's so thick and it's difficult to see where you're going. So being able to predict that is of huge importance. And fog is very difficult to predict with a lot of specificity. We're better at predicting where hurricanes are going to be and when they're going to happen than with fog. Fog, as many of you know, it's what got me into it at first, is also a water source, not only for ecosystems, but potentially for people. There are places around the world that are collecting fog for human use. And so that is a natural reason to study fog. How can we better use it and collect it so that we can use it, the water from it, for purposes that we need? On that same note, I think fog provides a way for us to get hope in times that are difficult. Oh, there's fog. Maybe we can get water from it. Wow. I think it inspires the imagination. It makes us think about what might be possible in ways that we hadn't before. Finally, I think fog is just a cool thing. It's very interesting. I love fog now. I know some people say, oh, Monterey, it's so foggy. I love that about Monterey, and I hope you do too. And I hope this was enough inspiration to get you started. There'll be more soon. The next videos that are going to be upcoming are going to relate to some of the equipment I use, and I'll keep talking about fog. But there's also a paper that I'd like you to read, and we can discuss it. And the paper is by Corison et al. It's on Canvas, and it talks about marine fogs. And one of my colleagues, Alicia Torregrossa, is also one of the co-authors on it. And I think that would be a really good place to start to read it. I'm not going to assign any reflection or pieces on it. Rather, read it and let's discuss it if you have questions. And I will also read it again. I've read it once, but it's been a long time. And every time I read these papers, I get more out of them myself. So I will also use this as an opportunity for me to refresh and strengthen my understanding and knowledge of fog too. Okay, until next time, take care.